So guys, I'll just quickly review what we did the last time. We looked at the fact that you can take data in a certain feature space, input space, and you could lift it into or transform it into some other space in which the data gets linearized. So we saw this example of a disk. Points on the disk are blue, points outside the disk are yellow. There are two ways of doing it. One was the transformation that I mentioned, x1 prime being the square of x1 and so forth. And what it led to is this triangular situation. So in this little triangle in here, everything is blue. Outside the triangle, it is yellow. And it was one quick way to see that yes, transformation leads to simplifying the problem, linearizing the problem, so that the decision boundary, as you can clearly see, is just a line, is just the diagonal line, right? The off diagonal line rather. So, and the thing to observe there was we did not necessarily lift to a higher dimension, isn't it? Then the other way is, and the same thing, just we can do it in multiple ways. So this other way that we could do it is, you could actually lift to a higher dimension. What you do is you create a variable x3, which is the square of the distance from the origin of each point. So you will, because it's the square of the distance, it is this thing, x1 square plus x2 square, it will have a parabolic shape. And in the parabolic shape, the blue points will be towards the bottom of the parabolic surface, and the yellow points will be everything above it. And so you can draw a hyperplane that we see, which is a constant hyperplane. X3 is equal to r squared, means at a certain height from the ground, which is defined by x1, x2, you have x3 constant, and this ring, this circular disk, is the disk that we see in the original data space. That becomes your decision. That is your cutoff point. That's your decision boundary. But how are we defining the decision boundary in a higher dimension space? We have linearized it because for us, it is this x3 is equal to r square plane. It's just a simple flat horizontal plane that cuts through the parabolic surface. And it's an illustration of the fact that you can take data, lift it to higher dimensions, and get away with linearizing it. And once you have that, you solve the problem. Right. Oh, there is okay, I noticed there's something a little bit off I should do. This is a minus b, a magnitude for polynomial kernel. I apologize. And this is some, not just one, some arbitrary number. So the kernel, if I defined, is the simplest way to think of a kernel is the very simple kernel is just a dot product of two vectors. But more generally, a kernel is the dot product of a dot product in the higher dimensional space. So it is actually here also there's a typo. I think I was being absent-minded last time. So what it basically, let me explain this concept again because I seem to have goofed a little bit. The kernel, the classic definition of a kernel is the kernel of a vector x and y is, first what you do is you take x and y, you take the points x, you take the point y, the x vector y, and you take them to some higher dimensional space, some space, not necessarily higher dimensional. People often say that the space is infinite dimensional because they always think of radial basis functions. Not necessarily, but you just go to some higher dimensional space, and this is another vector. It's a vector, some vector in a higher dimension space, and this becomes some vector in yet another higher dimension space, right? And basically, it is the dot product between these two. It is a dot product in that space between these two transformed points, right? That's it. And there,
yes,
things get much simpler. So that's a classic definition of a kernel. Kernel XY is actually nothing but the dot product in is basically a dot product in a transformed space between of the points. That's what it is. So
can we call phi as a transformation to that higher order space, or
yes,
in a sense?
transformation to the higher dimension space. So, for
Okay.
example, examples of phi are quite literally here.
Yeah.
If we
Square and all.
square and so forth.
Yeah.
These these are all the mapping functions. So the whole magic of kernels is that the surprising magic is that you can do the transformation at all. And by the way, these spaces are called, you will often hear the word Hilbertian space or Hilbert space. Hilbert spaces are very interesting. Now, what is the most simple intuition I can give you? Hilbert spaces can be infinite dimensional. These are functional spaces, right? So potentially infinite dimension. They don't have to be. Like, for example, in this example we saw, we got away with 2 dimensions, but they could have been higher dimensions, sometimes infinite dimension spaces. So for us to wrap our head around infinite dimensions is a bit hard. But the way to do that is carry your intuition forward from 3 dimensions. Hilbertian spaces or Hilbert spaces are something that physicists absolutely love because all of quantum mechanics, all of the theories of physics ultimately, more or less, have a deep connection to Hilbert spaces. And so these sort of arguments that you see, let's map it to a higher dimensional space, etc. This is very close to the work mathematical physicists do, which is why you often find that in machine learning, a large part of the literature or the terminology quite often is borrowed from theoretical physics, the concepts and so on and so forth, the mathematical physics, a lot of mathematics. So as always happens, math is and theoretical subjects are couple of 100 years ahead or 100 years ahead of engineering practices, because reality takes a lot of time to catch up, but the human imagination is way ahead. So a lot of this theory was developed a long time ago, and now they are proving to be very, very useful. Though 100 years ago, people didn't see all the practical use for it. Now it's all proving very useful. So simply put, as I said, the intuition is that think of dot products. Dot products capture a very rich relationship. Dot product in the initial space or in the target space, they are all wonderful things. We did that. Then dimensionality reduction we talked about. We know, just as a recap, the principal component analysis was wrapping up this data, shrink wrapping it in an ellipsoid. Now, you may or may not be able to do it. If the data is linear, you can do it. If the covariance matrix if there is a positive covariance or a negative covariance, you can do it. But sometimes the covariance is 0. Like, for example, in the data set 2, we noticed that you won't get much covariance because sometimes it's positively correlated, sometimes negatively, and so on and so forth. So what can you do? You can go to another space. You can use the kernel mapping, go to another space where the data gets linearized. So you apply a kernel mapping to go to that space. Once it is linearized, then if you're lucky, you can then do PCA in that space and actually come to a lower dimensional space, right? Which is why I mentioned that it is a good idea to do kernel PCA. Right? The next thing we talked about is another concept, which is that of kernel distance, which is actually different. The meaning or the word, the kernel here is used in a slightly different manner. Here the kernels are distance kernels, and we applied it to the KNN. We realized that when we take k is equal to 1 nearest neighbor, the decision boundaries are very, very, you notice that they have high variance. On the other hand, when you take k equal to infinity, then the decision, or k is equal to 20 in this case, the decision boundary is just meaningless. It devolves to the baseline situation, the majority situation. So somewhere between k is equal to 1 and k is equal to 20 is the perfect answer, is the best value of k. K is the hyperparameter of your k nearest neighbor algorithm. And it has been obviously a way to find that. You can try to find it. As you increase k, you can see that the green line is better, the red is perhaps not so good. It starts getting bad, and by the time you reach this orange line, it becomes, or the Indian red line, it becomes sort of terrible. So you know that the uh, here the best solution potentially is the green solution, and you discover that through obviously cross validation in the data. Now, one of the ways to mitigate this whole business of finding the perfect K is that you can use a distance kernel. You say that the immediate neighbors have more influence than the far off neighbors, right? And so then the whole question is, what is your notion of distance? We talked about the Minkowski distance and the L norm. This is just a review of that. L is equal to half, looks like this, circle, circle. L is equal to 3 and L is equal to infinity, the infinite norm. Minkowski distance is something that you should really review. Oh, by the way, I didn't post those notes, the ones that I showed you guys from my book. I'll post it to Slack. Then the K nearest neighbor. So obviously what you need is some distance function. Once you have a notion of distance, you need some function that decays with distance monotonically. It may not decay at all. It may just suddenly fall off, or it may remain constant, but something. But it certainly shouldn't increase with distance or swing back and forth. It must have a monotonic behavior. So people have come up with all sorts of distance functions to to have the best K nearest neighbors. We went through a review of that last time. If you remember, we covered about half a dozen or more distance kernels. Mostly the parabolic kernel tends to do quite well, but almost all of them do equally well. When you're trying to squeeze the last bit of performance or out of the model, then the last thing you do is you tweak and you pick your kernel. But broadly speaking, the kernels, in the beginning, the last thing you should worry about is which kernel am I using, right? Focus on cleaning the data, getting your distance measure right, doing all those things right. Then at a later stage, when you are beginning to do quite well with your KNN, kernel KNN, then also search for the best possible kernel. That brings up this whole thing about hyperparameter search that I would like to talk about today. See guys, do you notice that in ML100, there were not that many knobs to turn? You had linear regression, logistic regression, and so forth, LDA, QDA. They did not have too many hyperparameters built in. In fact, there were not any hyperparameters. But in ML200, we are sort of infested with hyperparameters in all our machine learning models. So the machine learning models say that if you tell me what the value of K is, we can build the best K nearest neighbor model for your data. But you have to find K. So what you have to do, you have to continuously go search for the best value of K, right? But then you have another dimension, which is the best kernel. So now you have to search in two dimensions, the best kernel and the best K. Now, usually what happens is a kernel KNN, they sort of mute the importance of the hyperparameter K. It still matters, but it doesn't matter so aggressively. So for example, the best K and the neighboring K values would all give more or less the same accuracy or the same performance, but now you certainly do have a problem. You have to find the best K and you have to find the best kernel to use, distance kernel to use. So you're searching in two dimensions, isn't it? And now suppose I had a few more hyperparameters in some kind of a model. Let's take random forest. What were the hyperparameters there? Well, we are building trees. So how many trees to take? Well, there the simple answer is take a lot of trees. I start with typically 400 in most situations. Then and go up from there, depending on the complexity of the data set. Then even for very simple data set, I'll take 100, 200 trees. But then the depth of the tree. How deep should the tree be, right? Each tree that you're building, what is the max depth that you will allow? That is a hyperparameter. It can go all the way from 1 to surprisingly large. You can go whatever depth. Then at what cutoff, like how many points do you want to leave in the leaf node before you stop splitting? You can ask whether I use Gini or Gini or entropy as my impurity measure. isn't it? So there are quite a few. And the other thing, of course, in random forest is at each split of the tree, how many features are you, what subset of the features, or what, more formally, what subspace in the feature space should you consider for splitting at each split in the tree? You don't want to take all the features, but how many features do you want to take? Just one feature, two feature, three feature, all 100 features, square root of the number of features, which would be 10, log of the number of features. These are all choices to be made. So, and at the end of the day, in the more general situation, in practical situations for one data set, some of the hyperparameters may matter quite a bit, but for some other hyperparameters may not matter at all. But a priori, before you do this experiment, you don't know what the situation is. Are we together? You don't know that. So what do? You have to search. You have to search this hyperparameter space to find the optimal combination of hyperparameters. But by now you realize that the choices are many. It is a combinatorial explosion, even if you take discrete values for the hyperparameter. So for example, if you take the depth of the tree is discrete, 1, 2, 3, 4, 5, and so forth. The number of features, max number of features to consider is discrete. The Gini versus entropy is again a choice, binary choice. Number of estimators is again up to you. These are all discrete. But let us say that in each case, you had a choice of about 10 possible values. By the time you have 4 hyperparameters, you realize that 10 times 10 times 10 times 10 is 1,000. So what you're doing is you're building 1,000 models to find which model is the best on cross-validation, isn't it? So that's a pretty aggressive computational load. So this way of brute force, are just creating a grid of the values and searching for it, used to be called the grid search method. The grid search method for hyperparameter tuning has been a classic. It is also a staple diet for interviews. So should you go for interviews and your interviewer says, well, what is grid search? Now you know, or the other way they can say is, how do you find the best values for the hyperparameter? So quite often they're expecting you to say grid search. And so you should start by saying, well, this is the way you could do it. But remember, this is not the optimal way. But then the other thing you could do, for reasons that we'll understand later, or maybe today itself if we get time, you can actually do randomized search. Take random values in each of the dimensions, hyperparameter dimensions, and then search. And then what you do is, once you find the best value, then you search in the neighborhood of that value to find even better values and so forth. You sort of zoom in. You can do that. That's called randomized search. It is, from experience, we now know it is better than this brute force, grid search. And lastly, these days, actually, there's quite a bit of theory on doing this in an optimal, in a much more efficient manner. And that is the domain, or that's one of the topics that we'll cover in automated ML, like ML. One of its main burden is, how do you do optimal hyperparameter search? Because you are not just searching along the hyperparameters. Remember, you're also searching along many algorithms. So for example, if it is a classification problem, then given the no free lunch theorem, you don't know which of the algorithms, which of the classifiers would be best. And each classifier comes with its own bag of hyperparameters, isn't it, guys? So the search for that becomes computationally very, very expensive. You need a systematic way to go about doing it. That is the new frontier. I would like to, we are running out of sessions, of course, and the syllabus of this course, we have 2 more topics, regularization and gradient boosting, both of which I would like to cover before the course is out. So we'll do automated ML in one of the extra sessions. We'll certainly start the boot camp with automated ML. So anyway, that's the summary, guys, of the last time. I would like to now move on to the topic for today, which is a continuation of what we talked. Now, today was supposed to be lab. But I thought about it and I sort of changed the decision. I felt that regularization is such an important topic, we cannot miss it. So we should do it today. And we should move the lab work to a regular. We'll do it over Saturday. So I swapped it. I said we'll do regularization on the weekend. No, instead we'll do it today, and we'll do the lab session over Saturday afternoon. I hope that is all right with you. And the boosting is also an important topic. It needs its own lab. So the next week we'll give to boosting and to its lab instead. Okay? The recommender we are going to anyway cover in the math course. So it will get covered. We don't need to worry about that. This is the way we do. So let's do it properly so that we get to do a lot of labs in each of these. Today, because we have already covered support vector machines and this notion of kernel distance is a bit theoretical, there was no very explicit lab that I could have given. So instead I decided I'll do regularization so that regularization lab is really important to do, and we'll do that on Saturday.
Sure.
Any questions, guys, before we start?
Can I ask a question?
Yes, please go ahead.
Yeah. So when you say, you know, we can go to higher order space, right? But if we do not know that space, like let's say example of size and weight for cow and duck, right? But we want to go to higher order space, but we do not know, let's say, color or other thing. Then what do we do then?
No,
Right?
no. See, you have to know that ultimately the higher dimensional space is manufactured out of the input space, the input space. So if you don't know, the machine learning algorithm won't be able to discover. See, it doesn't know what it doesn't know, right? That's the problem with all machine learning algorithms. Remember, we talked about the irreducible error in ML100 introduction. Right. But that is the irreducible error that you can't get away with. It is true with human beings also, you know. When we believe something is to be true, we base that judgment on what we know. But there remains the fact that we don't know what we don't know. We can just be aware of the fact that there must be things we don't know. Right? I hope from one of the things we learn here is that what we don't know may fatally compromise our understanding. It's almost, it is obvious, but it is the irreducible error in machine learning.
Correct.
And that no algorithm will be able to surmise. You have to bring it to the table.
So I think question is that, you know, when you say for kernel, you do not have to know that space. All you have to do is dot product in that space, right?
That is true. The kernel trick is, see, what happens is that some of these ways to map are quite powerful, like linear and polynomial are good. And so for example, you know that polynomial will work for the river data set easily. Right? Then linear would have worked easily for the straightforward classifier one problem. Then the radial basis function works for a vast class of problems. When you use RBF, you're actually talking of infinite dimensional spaces. At that particular moment, the infinite dimensional space is so rich, you're pretty much guaranteed a linear decision boundary, more or less, a very high probability that you'll solve the problem. Right?
Yeah.
Okay. The problem. So you don't worry about that. You take these kernels and go. Question that arises is, could you hand construct a kernel, a mapping, just as a feature engineering exercise? Think it through and give your own mapping to the higher dimension. If you can do that, all power to you. Actually, it leads to some very efficient solutions because computational runtime with the RBF kernel is quite high. You know, you're taking it to very high dimensions and you're searching for the solution there. If you can do it with your own homegrown kernel, the performance is better, even the computational times are better, and so on and so forth. But if you can't, RBFs are very powerful. Generally, they do solve your problem. And then the other interesting thing is that, obviously, it is the dot product that matters. The kernel trick, the heart of the kernel trick, it is not a theoretical breakthrough, but it is a computational sort of a cheat way or a shortcut. You manage to not discover the mapping function itself, but you discover that whatever mapping function there is, you discovered the dot product of it. And if you can reformulate your problem in terms of dot products, in terms of kernels,
I see.
you have a winner. And that is why kernels became so, people said, wow, that is amazing. Given that that is true, can we then reformulate a large class of problems as kernel problems? Right? That's how the whole kernel method thing started. And they were very, very surprised actually. You can write many things, and if you, with a little bit of thought, you can rewrite it as a kernel function.
Mm-hmm.
Amazing, just surprising. It just shows that how powerful dot products are.
I see.
So a lot of work in that space.
Thanks.
Any other questions, guys? So guys, remember that we are coming to the close of the workshop. We still have two important topics to cover: regularization and boosting, both of which needs dedicated labs. So we are one session short. So I use this session for regularization, and we will have Saturday. So do treat it as a mandatory session, guys. We must finish the syllabus, which is that we must do the lab in regularization, and next week we'll give to boosting. So, all right, so I'll move on to the regularization now. What is regularization? See, when you, and I'll take the example of a polynomial regression to sort of motivate the concept of regularization. Suppose I give you data, let's say that, and let's take a simple situation of X and Y, where we are saying we are in search of X is equal to some function. And let us say that there is a ground truth you don't know. There is a ground truth. This is the ground truth of the data. This is ground truth of the data. And let's say that you have these points, right? Let me take these points here. And let me say, now I'll just take these few points. I hope I can illustrate the problem that I have with this. So I will keep these points, and let's see what sort of curves we can draw through this. One thing you could do is you could say, hey, okay, again, let me be clear with the terminology. G is our ground truth. It is that which you don't know. It is the function that has actually produced the data. What is our task? Our task is to build a machine learning model, which is, let me just make it Y hat, right? You're going to pick a hypothesis, going back to the basics, hypothesis function, such that Y hat is approximately Y for most values, isn't it? In other words, Y, the real value is Y hat plus some error, and you want this error to be small. A good model is one that makes fairly accurate predictions that are close to reality, they're close to the real values of Y. Now, if you take the case of polynomials, polynomial regression, you realize that you can write fx as beta naught plus beta 1 x plus beta 2 x squared plus, and you can keep going on to beta n x to the power n. Right? Do we remember this thing, guys? This is your polynomial regression equation, approximating the data, trying to fit the data to this polynomial.
Yeah.
Now the question is, what is n? Here, the big problem is, what is n? What is the best n? Trouble is, if you take n essentially becomes the hyperparameter of the model, isn't it? It has. And so you have a headache. You have to build models over and over and over again and see which value leads to better results. right? You can keep trying. But so one of the questions that you can ask is, let's see what happens and see if there is a shortcut through this. If I take n is equal to 1, what will this look like? N is equal to 1 would be this, right? In simple terms, what would you call that?
Straight line.
Straight line that is like this, isn't it? This is n is equal to 1. For n is equal to 1, it is the straight line. For n is equal to 2, it would be some parabolic curve. I don't know if this is exactly the one, but we'll assume that this is the one. N is equal to 2. Then for n is equal to 3, let me take another color. Why am I having this color? This color. So n is equal to 3, maybe that it is this one, right? Let me make the points big and bold so that we remember those points. And then what about n? So it needs 2 bends, n is equal to 3. What about n is equal to 5? What will happen? What will happen is, as you go to higher, and I will pretend, because we should programmatically draw this out to see which one fits, but just humor me. This is too fat. Let me take something like this. Okay, so if you were to take this, it would be, it needs 4 bends, right? So it would be something like 1, 2, 3. Let me take it like that. I'm just motivating the example. If we actually did it in a model, it might look something different. Maybe I should have done before I came here. So this is n is equal to 5. What do you notice happening? And let me, without actually having done that, let me say that, suppose I had done that for n is equal to 10, what would it look like? So now I need 9 bends, and your data will begin to look, oh gosh, it's too fat again. Your data will begin to look like this. It will look like, and more than that, actually, it will look like this. Something like this, because you need 9 bends, 1, 2, 3, 4, 5, 6, 7. Actually, I didn't introduce 9 bends. We need to make it even more curvy. So who knows, we need to add a couple of bends right here. Make this more like this. So what happens is, if you go to n is equal to 10, you have a complete fit to the data. It seems to go through all the points, isn't it? But do you think n is equal to 10, something like this, is the correct solution? What does your intuition say? What is the problem that this model is having?
Overfit.
It has overfit the data. So what happens is, the more parameters you have, polynomial terms you have, the more knobs you have to turn in the data. It's a very flexible model. I'll give you an intuition. Imagine that it is a sort of a, what do we call it? Are you familiar? Well, think of it as silly putty, something like silly putty, right? If it is very stiff, you can't bend it. It's like the n is equal to 1 line. Now, gradually, as you make it more and more pliable, you can bend it more and more, isn't it? And so you have bent it. Actually, silly putty is a bad example, but think of something that has some degree of elasticity to it, right? The more elasticity it has, the more you can bend it. So the higher degree of polynomial, the more pliable it is, the more you can bend it. What happens is, if you take a high degree polynomial, you have too much elasticity. You can just fit that polynomial, that curve, to the entire data perfectly. But you know that that data is just a representation. You take another sample of the data, and this curve will be all wrong, isn't it? You will end up drawing a completely different curve to this data. So how do you cure this problem? This problem is the problem of overfitting, isn't it? So you do know that flexible models, do tend to fit the data, but you don't want it to overfit. So just as a reminder, the total error of a model, model is equal to the bias error plus the variance error plus what else? The variance error plus what, guys? Do you remember? What is the other?
Irreducible error.
Irreducible error, right? Irreducible error. Thank you, Kate. Reducible error. It is the captures noise as well as that which you don't know, that which the model doesn't know. So see, if you try to reduce bias, variance increases. Are we together, guys? That has been the bias variance trade-off. So let me draw the bias variance trade-off again. And by now, you should be quite familiar, I hope, with this. So as you increase the complexity of the model, for example, in the case of polynomial, as you increase n, the errors, right? The bias error of a model, as you build more and more complex models, will keep going down like this, right? What about the variance errors? The variance errors will start actually, let me use another color so that I can use white for the final solution. So let's say that your bias errors go like this. They keep on decreasing the more flexible you make the model. Your variance errors, on the other hand, begins to go like this. And let me give names to this. Errors, and this is errors. So you know that somewhere in between those 2 points is the perfect line. It is this line. And let me use white itself, but a thicker version of white, hopefully. So the total error, if you add these two up, you notice that it goes like this. And whatever the value of k here is, this value, this is the best model that you can build, right? So this is the best approximation, right? So suppose Fn, I will say, of degree n, to the ground truth. It is the closest you can come to the ground truth. And this error that you're left with is obviously the part that you can't get rid of, right? It remains at the end of the day. It's the residual error for you. Are we together? It's made up of whatever little bias error remains, whatever little variance error remains, and the irreducible error. So as a recap, guys, does this ring a bell? Are we familiar with this so far? We did that just a couple of months ago in ML100. So this is it. So now the question is, here you have this big surge from here to there. The question to ask is, what happens if you make an overtly simple model, a biased model, a step model? Its errors will be hard to deal with. It's a sort of fatal. You can't get rid of that. On the other hand, if you make your model too complex, right, too flexible, the question that arises is, going back to this data, do you notice that the complex model n is equal to 10 or n is equal to 5, a green and the pink lines, they have too many oscillations, right? They seem to be oscillating quite a bit unnecessarily. So it is tempting to ask, can we apply a damping factor? Can we dampen the oscillations? It's bouncing around too much in the feature space, this curve. Can we reduce the bounce? Can we dampen it? Are we together? Because if we could dampen it somehow, then it could solve a problem. We could start with a flexible model and we could dampen it down. So the basic idea is that, can we start with, let's say, a green line or the pink line, but somehow dampen it down to the yellow line. Now the yellow line is the perfect line, right? In this case seems to be the best model. That is n is equal to 3. Isn't it, guys? So the idea is, suppose I took a more complex model like n is equal to 5. Can I bring in some mechanism that, in spite of my taking a more complex model, the extra degrees, the extra flexibility somehow magically disappears and it begins to approximate the yellow line, the yellow curve? That is the intuition of this whole problem, or this whole bag of tricks called regularization, this technique called regularization. Are we together? It is also called shrinkage methods. In fact, your book calls it shrinkage methods. The statisticians call it shrinkage method, shrinkage. Now, the machine learning crowd tends to use the word regularization more often. Shrinkage means you shrink all of these oscillations and you make it look like that yellow curve. Right? That is what we will learn to do. But for us, so the answer to that is yes, you can do that. It turns out there's a very elegant way of solving this problem. And the solution to that comes from a field. It's a very simple bit of mathematics called, and it is a problem in constrained optimization. Now, optimization. I already sort of introduced you to the concept of constrained optimization in the support vector machines thing. In other words, find the maximal margin hyperplane constrained by a certain budget of mistakes that you can make. Remember? So we will use same things of constrained optimization today. But before I go into the mathematics of it, I just wanted to say that, see, this theory is very elegant. It's one of the crown jewels, actually, of linear methods. The fact that you can take a fairly complicated polynomial, which is still considered linear because it's linear in the polynomial terms, and then regularize it and get to the solution. Regularization is one way. There is another way, actually, to solve this problem. The other way is to just bring the other way. Let me just write it in a sidebar. The other way, other option, and probably the preferred one, or probably preferred, something is wrong with my preferred, it's a spelling. Preferred way, the preferred way would be what? Get more data. Get more data. So what happens is, if you get more data somehow, it is possible to get more data. Suppose you have points like this. Lots and lots of data. And I hope, I'm not making enough number of dots, but imagine that this is very densely packed with data here. But then what happens is, the curve that tries to overfit, it won't get enough flexibility. It may sort of ripple around a little bit, wobble around a little bit, but it will ultimately look like even a high degree polynomial will look like this. Do you notice the small wiggles that I have put in the line? There may be small ripples or wiggles in there, but broadly speaking, because a 10-degree polynomial needs 9 wiggles, it will still be there, but it will be unnoticeable, right? So what has happened is, you have given it a lot of data and it is forced to fit with a lot of data. So overfitting disappears or gets muted. So here, overfitting or high variance, if you want to put it this way, the high variance gradually is suppressed. right? So you can, and this is, by the way, the preferred way. If you can get more data, then do it. So what is the catch here? Why not just use more data? Why develop a whole new theory of regularization and so forth? Can somebody guess?
It can be expensive to get data.
It is expensive to get data. Yes, that is very true. That's one reason. See, one
Or
of the
it might not be available. Like if it's a rare cancer, like the data might not be available.
yes, that's the point. In a lot of fields, data is very, very hard to get, and you have to make do. You want to model with what you have. You can't say that it's like, asking for food on a silver platter. Well, there may not be. So you do want to make do with what you have, and more data may not be available. Another way to look at it is, see, remember I told you that the higher dimensional spaces are very sparse. No amount of data will look enough because all the data disappears in that space. So overfitting happens when the data is sparse and you're fitting a very flexible model to it. When you do some of these modern algorithms, let's say a deep neural network, which you will do shortly in the next workshop, can you guess how many parameters we're talking about? Here we are talking about a polynomial of degree 10. In a typical deep neural network, how many parameters do we typically talk about?
A few millions to billion.
Exactly. So if I am right, yeah, millions of parameters, even the basic ones have millions of parameters. And then I think GPT-3 has what, 500 million parameters or something like that. So the parameter space is just ginormous. So you might come there with 10 million data points, but your 10 million data points are a drop in the bucket as far as that huge hyperparameter space is concerned. So overfitting is a very serious problem there. This getting to wrong answers, so overfitting problem. And so you have a lot of overfitting errors, high variance errors in your problem. And so the theory of regularization, you need to find a way to regularize. So today I'll hopefully, based on how much time we have, I will teach you at least how many techniques, three. I'll try to teach you at least a few techniques of regularization. And on Saturday, we are going to do a lab on those techniques. So how do we do that? Let us go back to the basics. Suppose you have a function y. Let's go back again, write down what we wrote before. We are trying to find a function y hat is a function of x. Right? And you know the ground truth, y is actually a function of gx, right? So you know that y is basically y hat plus some irreducible, some errors that get made in your model. And your pursuit is to find an fx that approximates the ground truth, right? This is our ground truth. How in the world are we going to do that? Let's go back to basics. We have a loss function, the error function. We know that each time so let's look at regression as an example. Yeah? And this will generalize over to classification also. What is the error term for each data point? The error is equal to y minus y hat, isn't it? Yeah. This is your residual. Now your sum squared error was summed over all I. Do you remember that, guys? This was your sum squared error.
Yes.
Now, given this, and now what you can do, this error, if you just expand it out as y minus y hat I square, this comes to, and let's do the little bit of mathematics here. This comes to yi minus, what was y hat? Beta naught. Let me just take the term beta 1, x1, right? Plus beta 2, x2, etc., etc. But let me stay with one dimension for the time being. It is this error. Do you agree? And we can sort of add more dimensions to it. It's not going to change the thing. And obviously, I shouldn't forget my summation I. This is your error term, guys.
Yeah.
Any mysteries here so far? So when you have this, you know that when you are doing your problem, data is fixed. During learning, data is fixed, of course, because you're learning on the data. So the values of x and y are not changing. Xi, yi. Changing. So this E, what is it really a function of? E is therefore a function of
beta naught and beta 1.
Yes, beta naught, beta 1, isn't it? This is what is really happening here. Let me remove this sidebar line here. This is it. So I can write, therefore, this equation as E beta naught, beta 1, and then I can go to beta 2, etc., if I so wish, is the summation over square of yi minus beta naught minus beta 1 xi, right? And if I want to add higher order terms, I can do that. But let's stay with one dimension. This is what it is. Right? Now, if you expand this out for each of these terms, you'll realize that it expands out as yi square plus a beta naught square plus beta 1 x1 xi square, right? Plus minus 2 beta naught yi,
Each
right?
pair of terms.
Minus 2 beta 1 yi xi minus, and obviously we'll have to put a big summation over all of those. And what else is there? We missed one more term. Minus,
and
plus
beta naught, beta 1,
beta naught,
xi.
beta 1, yeah, 2,
xi.
xi, right? So guys, if you look at this equation, right, it's a bit of a long set of terms, but do you know that what is the highest power of beta that you see here in this equation?
Beta naught square.
Is the square terms, right? Beta naught or beta 1 square. So you would agree that this equation is quadratic, i.e. E beta naught beta 1 is, and this is the important thing, quadratic in beta. Isn't it? It's quadratic in the betas.
Yeah.
So now quadratic curves look like, how many bends does a quadratic curve have?
1.
1. And so in higher dimensions, how many, the generalization of a curve is a surface or a hypersurface, in this case just a surface. So what will it look like? Let's look at this axis, error. And this is this. This is beta naught, let's say, axis. So now remember, we are not in the data space, we are in the hypothesis space. We keep using this word, hypothesis space. We are in the hypothesis space. So here, if you remember, we talked about this. This is just a recap, guys, of what we did. This is for each value of beta naught, beta 1, there will be a certain amount of error, right? And this is your curves. And there will exist a point, a perfect beta naught. Let me just call it beta naught, beta 1 with a tilde on it. The perfect values, the best values, the optimal value where E minimum of E minima is achieved. In other words, what you are searching for in this space is this point, beta naught, beta 1, represents in the beta space, right? Let me just write it as a beta, well, tilde vector, but okay, I'll just write it like that. This is what? It is the point where it is that value of beta naught, beta 1, where this achieves the minimum. The error achieves the minima, right? That's just a summary way of putting it. what value, what argument of beta naught, beta 1 will minimize the error. That represents our point here. Right? Let me draw this picture a little bit better. We see the parabola. Actually, I need a bigger screen.
That is AVG or that is ARG?
Argmin. Argmin.
Argmin, okay.
This word is, let me say, arg. I mean, the reason I introduce this word today is because you'll encounter it in books. So gradually you notice that slowly I'm introducing the mathematical notation in little droplets. So which value of the argument, what are the arguments to this function? Beta naught, beta 1? Right? So which argument will minimize the function? Argmin means, let me write this word down. The definition of argmin. Argmin of a function is those argument values that will this is the definition of Argmin, by definition, def. So likewise, you can define the argmax. If you want to maximize something, the counter term or the equivalent term would be argmax. Argmax would be those values of the argument that will maximize the function. So the words like argmin, argmax are pretty common in this literature. Argmax. These words, they keep occurring in the ML literature. Right? And this is just, do you realize that this box that I have here, it is a very succinct way of saying, what are we searching for? Our optimization journey is to find this thing, beta naught, beta 1 tilde, the beta tilde. Does that make sense, guys? We are just recapitulating what we did in ML100 here. But if you have not understood, speak up, guys. I'm not getting enough feedback. You want me to repeat? I'll be happy to repeat.
Asif, I might have missed it, but is this beta 0 and or the beta 0 tilde and beta 1 tilde? This is a specific case for one error, right? Or
Yeah. So what happens is that, see, in your model is this, beta naught plus beta 1 x, right? Based on this, we create the error function, beta naught, beta 1, error function. In the hypothesis space, it looks like this surface. Right. This is the error surface. What are you looking for? You're looking for the point of minimum error.
Point, or it is for all the summation of the data point?
It is the summation of all the data points. E is, yes, you're right. See, E is the summation over the errors from all the data points. You notice this. The definition of E is that it is this. Remember, we started out with this derivation. E by definition is the total error over all data points. So this is the total error, which is the sum of square of all the residuals. And then we expand it out mathematically. And then we notice that when we expand it out, it's a quadratic function in the beta naught, beta 1, right? So in the hypothesis space, whose axis is beta naught, a parameter space, hypothesis space or parameter space, hypothesis space, it looks like this parabolic surface. Is this, did you get that? Like, should I re-explain?
No, I understand the parabolic part. But when we are trying to minimize, so is it getting minimized for only one data point, or how can we ensure that it is minimized for the summation of the data points?
See, E is a function. E is derived from the data points, no? Summation over all the data points. But once we have created the summation over all the data points, the only knobs that you can turn are the beta naught, beta 1, right? Because the points are there, you have calculated the total error for any given value of beta naught, beta 1, you know what the total error will be.
Okay.
And so you're trying to find that point, right? This total error is also called the sum squared error, SSE, sum squared error. Sum squared error.
Got it. Yeah.
Got it. Okay. So now comes the theory. So this is a recap of what we did in ML100. Here is the intuition. See, what happens is when you add higher degree polynomial terms, so you're expanding your hypothesis space, isn't it? So as polynomial, go ahead.
Yeah, the definition that you wrote, the argument of a function, is those argument values that will minimize the function. I didn't get this last part, that will minimize the function. Are you, by that, do you mean the length of the function?
Example. Let us take one dimension. Y is equal to x squared plus 10, right? Now, tell me at what value this function is, y as a fx. Let me write it this, y or fx. So what value, what will minimize of x will minimize the function?
0.
X equal to 0.
Yes. So x is equal to 0, right? So you say that x is equal to 0 is the arg min of fx. This point, the value x is equal to 0, is the arg min of the function. It is the place where function is minimum. But the minima of the function is what? Minima fx is what? That will be equal to 10, because if you put x is equal to 0, it will be 10. Right? So the point x is equal to 0, fx is equal to 10 represents your minima. Represents the, and you can call it y, and so you can say y is equal to this. Does this look simple, guys? Right? So if you plot it out, it will look like this, and this will be 10. So this point, x is equal to 0, represents your arg min, the point at which this curve achieves its minimum. So, so we will write it. So the way you would say that is arg min, if you were to use this notation, arg min, that is x, fx is equal to 0. In other words, the value of x that minimizes the function is 0. Is this getting any clearer, guys?
Yes.
Right. So this is the meaning of arg min, right? So for example, let me deliberately complicate this problem. I'll make it x is equal to 3. Now what value of x would minimize this problem? Can you guess? 3. So because 0 is special, I don't want to use 0 here. So this is it. And so this would be, arg min would be 3 here, and arg min here would be 3, right? And on the other hand, the min fx would be 10. The minima that you would achieve would still be 10. That's the concept of arg min, guys. So what we are searching now, let's bring it back to our real life. What we are saying is we are finding that hypothesis in simple terms, those parameter values, beta naught, beta 1, that will minimize our error term. Is this, think about it for a moment. Is this clear, guys? If not, I'll repeat it again. Anybody who wants me to repeat, say so.
Asif, can you repeat it again?
Yeah, see, what happens is, let me put it in a slightly different way. See, when you have a total error, that error is associated with some hypothesis, some value of beta naught, beta 1, some parameter values. because your hypothesis is parameterized by beta naught, beta 1. So any value of beta naught, beta 1 that you take, there will be a certain degree of error, right? In simple terms, in this beta naught, beta 1 plane, this plane that is there, right? This is your hypothesis plane, right? Let me call it the hypothesis plane or space, whatever word you want to. For every point here, there is a certain degree of error. Any point you take associated with it is a certain degree of error, isn't it? And so what you're trying to do is finding that point where the error is the least, because you're trying to build a model which makes the least prediction error, isn't it? And therefore, that is your that's your best solution. That is the best you can do. You can just learn your way towards that. And just as a recap in ML100, what we would do is we would start at a random value, and then we would do gradient descent here. So in other words, around this point, there used to be this, remember, this is the projection of these shadows of these circles, or these are called contour maps. Here, do you remember this, guys? I hope you remember this, because we'll use this to move forward towards regularization now. That this
Yes.
error surface, yeah, it's shadows of these circles, these contour maps, sort of level surfaces are these. And so you take a random point, suppose you start here, it has a huge error, and what you're looking for is you're finding your way
Center to the minimum.
center. You're just finding your way through gradient descent towards the center. This is your gradient descent.
Asif,
Yes.
then is the argmin sort of either very close to or just the irreducible error then?
No, not necessarily. See, even when you reach the minima, you may have reducible as well as irreducible error. Or what does that mean? See, for that model, it is the lowest error. But you could build a better model. You can dial in the complexity, take a different value of n, and so forth, isn't it? So it still has. So in other words, there is still residual bias and residual variance, along with irreducible, present in the model, in the minima.
Okay.
In other words, let me go back to the terms where we define the error. Where is it that we define? Yes. Bias errors. Yes. Look at this pink equation. See, irreducible error will remain. It represents that which you don't know. But if you look here at this optimal point, right, do you notice that the pink line is not zero? The value of pink is not zero. There is still bias error as well as there is yellow line is not zero. There is also variance error. Isn't it?
Yeah.
That's the thing. So even at your best model points, there is still some bias error, some variance error, and there is irreducible error. In fact, we did decision trees. What happened? Even with pruning and so forth, it was not possible to reduce the the variance errors too much. No, it's still stuck there. So we went to random forest, which made the thing a little bit better. There are many adaptations of random forest that try to solve that problem of overfitting. So that's that. So far, so good, guys. So let me recap what we just did. So we are saying that in the hypothesis space, first of all, okay, recap of what we just reviewed. Recap of recap. Error term, which is a function of beta naught, beta 1, etc., is equal to y minus beta naught minus beta 1 x I square. This is the sum squared error. And as somebody asked, over all data points. Now, in the hypothesis space, so the data exists in real space, right? Whatever the data looks It exists in the XY space, the real data space. But in the hypothesis space, where the coordinates are, by the way, a bigger drawing board is on the way, so I won't have to scroll up and down so much in a few days. Beta node, beta 1 error. In this space, the hypothesis space, we have a parabolic or a surface, or this convex surface, which achieves a minima at some best point, beta. I'll just represent it as beta tilde. Yeah? You can assume beta naught, beta 1 is built out of it. Beta naught, so beta 1. It is this, but I'll just represent it as a beta tilde vector. Right? This is what exists. And these things, they form contour lines. These, if you project down this, there are these contour lines in this hypothesis. So if you start with some random point, you will have to find a path going to this. And this journey is your journey of gradient descent. So we won't recap that. I mean, but if you want to remember the rules of the gradient descent, it was beta minus alpha grad of E, and the derivative of E. So this is your ML100. So go back and look at the notes. You'll see that this is your gradient descent step. Gradient descent step. In other words, go opposite to the gradient, right? If you're here, go opposite to the gradient. Actually, you know what? Let's go through the derivation of this gradient descent. How many of you would want me to recap the gradient descent step?
Can you do it, please?
Okay,
Yes.
let's do that. But if you do that, it's 8:25. Guys, give me about, let's take a break actually. Okay, let's take a 10 minutes break, 10-15 minutes break, and then come back. So to motivate this, I will just take a simple example of what a gradient, about gradients, to illustrate a point. See, if you have a function, let me take a function, y is equal to, basically your fx, that looks like this, right? It could, for example, be something plus something x squared or something like this. This is your x-axis and this is your y-axis. Right? I want to explain what gradient descent is, the basic intuition. And again, I'll move a little bit faster because we have done this before. Gradient descent is a way to start from any random point and reach this destination, this point. What is this point? This point is your arg, in our new language, argmin of fx, isn't it? It is that special value of x tilde, where this function is minimized so far. So how do we reach this? How do we come to that? There's a very interesting thing to observe here, and that observation has to do with the slope of the line. Look at this. What is the slope here, guys? At x tilde, the slope is it flat, rising up, or falling?
Flat.
It's flat. Slope is 0. Now, the definition of slope is, let me just remind you, the definition of slope is increase in height for unit movement, unit increase of x, unit increase of x. So suppose I'm here at this point. If I make a small increase, delta x increase delta x, and this is the step forward. So I would go from the point, this point, to this point. So have I increased or decreased in height? So when I go from this point A to B,
Decrease.
let
Decrease.
The negative slope.
x and B is equal to x plus delta x, right? The height decreases. So you say that in the vicinity of x, the slope is negative, right? The slope, so y decreases in going from A to B, i.e. from x to x plus delta x. Isn't it, guys? So y decreases in going to that. And so the conclusion we have is slope is therefore at A, slope is negative. Negative. Now let's look at the point, this point. Let me call this point x prime, right? Or at x prime, if I go a little bit, a unit distance forward, delta x forward, I go from, let's say, C to D, right? So when going from C to D, from delta x prime, C is equal to x prime to D is equal to x prime plus delta x, right? Do we increase or decrease in height? What did we agree?
It increased positive slope.
Yes, it increased. So we went up, the height increased. So slope is positive. Slope is also called the derivative of a function, right? Slope is called the derivative of a function. So we can say it's usually written as a dfx dx or a dy dx. And sometimes for shorthand, people often use a prime to signify, right? Pronounced as y prime. Right? They often use this. I wouldn't, because I tend to use x prime, y prime just for points. So I will not be using this notation, right? So not be using this notation, will not use this. Notation. So these notations are common, and I'm just recapitulating the calculus that you have learned in high school, and this is just a recap of what positive. So here the slope is negative. Negative. Here the slope is positive. Now comes an interesting thought, guys. At this point, suppose you are at A. If you want to, your goal is to go home, to find the optimal point, this, right? So suppose you are at A, and therefore this is the error. In which direction should you go to decrease the error, decrease the y? Should I go in the positive x direction or negative x direction at A?
Positive x.
In the positive x direction, right? So you can say at A, we should go in the positive x direction. Slope is negative. So dy dx is less than 0. at this point. What about B? At C, where is C? Let's go back and look at C. At C, if you are at C, guys, do you want to go C? This is the FC. And do you want to go in the positive X direction or negative X direction to decrease Y?
Negative X.
At negative X direction. At C, we should go in the negative X direction. Here, slope is positive. Is positive. So do you notice something very interesting? If the slope is positive, we want to go in the negative direction. If the slope is negative, we want to go in the positive direction. Isn't it?
Yeah.
And if the slope is 0, we want to just stay put. Isn't it? At this point, do we want to go anywhere if we reach this point where the slope is 0?
No.
No. If slope is 0, so let's write that condition down. At go nowhere. We are already home. Right? We are already home. So observe. So one of the things you can do is you can say that at any given point, to minimize the function, go the next value of X should be, or let me put it this way, the next value of X, that is, should be the previous value of X. In this case, you want to move in the positive direction, right? But the slope is negative. Suppose I did this, dy dx, and the slope can be a big value. I multiplied by a small number, a small step. I take a small step against the slope. The slope is negative. I want to move in the positive direction at A. Remember, once again, this is A. This is C. At A, slope is negative, dy dx is less than 0. Dy dx is greater than 0, just to remind you. So at A, what do you want to do? If you multiply the slope by a negative number, negative of a negative is a positive number, isn't it, guys?
Yeah.
And so you're taking a step in the right direction. Would you say that the next value of X next will be somewhere here? This will be your B.
Larger than A.
Right? It will be where you want to be. So this is it. Now let's look at this. At C, what do you want to do? Slope is positive. Once again, your next value of X should be a hop back. Here you want to hop, actually, let me make this hops more visible. Use another color. You want to move in this direction. Here you want to move in this direction, isn't it? So you want to do, at C, what do you want to do? Slope is positive. Once again, you want to go against the slope, the dy dx. Does this make sense, guys? If you take a little step like this, and alpha you can take as a very small amount, like 0.01. You take a tiny step, it's a tiny step in the right direction. And you can keep making those tiny steps till you reach home. Right?
Yeah.
This is your X tilde. So to go towards X tilde, to go here also towards X tilde. Is this obvious?
I think Asif, for your point C, you are missing an equal and X there, I believe.
Oh, right. Oh, I'm sorry. I forgot to write that. You're right. Thank you for pointing that. Huh? So minus the previous value of X minus the negative of the slope, because here the slope was positive.
Yeah.
Negative. And here the slope is positive. Right? And so you realize that irrespective of where you are on the increasing or decreasing slope, the general rule to take a small step towards home, towards x tilde, home is that x, your next value of x should be the previous value of x minus some small number, some small fraction of the dy dx, right? This is it. Do you see this, guys? I hope this is this intuition is clear to you from this. I'll recap. For any function, if you go against the slope, you're going towards the minima, right? So the rule is, I'll write it down. In other words, if you are going against the slope, you are going towards the, it's just many ways of saying the same thing. So now let's generalize it to higher dimensions. Suppose y is a function of x1, x2, xn. How do we generalize? Now there is no notion of dy dx because the question is, what is x? X is a vector now, right? And so it turns out that what you can do is you can say that suppose I have a surface like this, I can make a small step, like at any given point, I can either move a little bit in delta x1 direction or delta x2 direction. Let's say, okay, let me make it x1, x2, then I'll give I should reverse the order. Delta x2, x1, right? Are we together, guys? I can see how this function fx varies as I move in this direction or this direction, right? So you can say, we can look at the change in y as we move a step along one of the axes, variable axis. Isn't it? All you can do is take a small step in this direction or this direction. Each one of them will produce its derivatives. The partial, the slope specifically along each axis, keeping other, not moving, not changing along other axes. That's an important criteria. Not changing x value along other axis is called, it's a partial slope, right? It's sort of a partial
derivative.
It's just a slope. If I just change x1, right? So how much it changes, the value changes, but partial derivative.
Yeah, partial derivative. That's what it's called.
Derivative. This is what a partial derivative is. And the way we write it is, you'll see me use this notation, dy dxi, right? Or a dfx vector along this particular direction. You'll see these two notations often used here, notation. So then comes a very interesting question. Suppose I make a change from the unit vector x to x plus delta x. Means if I make small changes along all of these, if you make along each of these values, then what happens? How much change do I get? Right? It is worth asking, what is the value of the function x plus delta x? And that value actually can be represented, right, by saying that it is actually just as in the case. Okay, so let me, before I go there, let me bring up a concept. So if you put all of these, let's say that there are two axes, x1, x2, right? And you're looking at y as a function of this. So you will have dy, dy, let me just write it as dy, dx1, dy, dx2. Both of these you can write, isn't it? So there are two components here. If you treat these two components, now here's a magical thing you can do, and you'll see why. If you can treat these as components of a vector, see, x is a vector, x is equal to x1 I plus x2 j. This is how you write a vector,
Yeah.
isn't it, guys? The standard notation. And
Yeah.
it is also, but in machine learning, you don't tend to write I, j, k. You tend to write x1, x2, a column vector. A column vector. Vectors are written in machine learning as column vector, and it is absolutely equivalent to the same thing. It's just a different language in which we write it. So x is a vector. Now we notice that when you take partial derivatives, you can take partial derivatives with respect to each of the x's. So we can therefore ask, what is this vector? What is this? x1 dy dx2. What is this column vector, which is the same as dy dx1 I plus dy dx2 j? Right? What is this? It turns out that this is a very useful thing. It is very, instead of just like you can have a slope, it is the generalization of the concept of slope. It is this notation, nabla, or the grad. It is also called the grad or the gradient. These words are all used. Nabla is the Greek letter. So it's the nabla of y. It's called the gradient of y. And more generally, people can just write it as an operator, as an abstract operator. You say, this is just this. It is an operator that is waiting to eat something. 1 d x2. Do you notice that this is very funny? A partial derivative of what? Right? You haven't specified that. But so if you put y here, it will become this. Right? This is equal to, by definition, this is the partial derivative. This is called the gradient of y. Now, we realize that in ordinary differential equations, the y plus delta y was equal to basically x plus, it was basically delta x.
Function of x plus delta x.
So I wouldn't actually, let me not go into the calculus, just take it as a fact of life. Delta y in single dimension in 1D variable, one variable, is dy or dx times small change in x. The small change in y is the slope times the small change in x.
Yeah.
Right? Which is sort of intuition is, and it's very obvious here, that you are here. If you make a small step forward, the decrease is proportional to how big a step you made and how steep the slope is. Isn't it?
Yeah.
Yeah. So that's the idea. How much you lost in height or gained in height is proportional to that. So this is it. It's generalization. It's the change in y in a vector notation as a vector, let us say that, the change in a y, when x is a vector, is actually gradient of y dot product with small change in x, because now the change in x is a vector, right? You go from this point to this point, right? This is the x vector, x1, x2, and you made a small change, delta x. Right? And so it is given by this equation, small changes in this. Now, what does it mean? Let us study this gradient and we'll be practically done with so this is just the mathematical background to understand regularization. What does, if gradient is a vector, do you realize that gradient is a vector? Then where does it point? Vectors point in some direction, isn't it? So let us study that. Consider a circle. If you have a circle, let's take an arbitrary point. This point is P is XY, right? From the origin, the line that connects to this is the P vector.
Yep.
Is that obvious? So now, what is the equation of this point Y, right? At this particular point, do you realize that the equation of this function is fx? Actually, let me use the notation of x1, x2.
Yeah.
Not use y. x2, I can write it as x1 square plus x2 square, right? And the circle is fx1, x2 is equal to some constant, r squared. Would you agree?
Yeah.
It is just a constant, what you call a contour line of this function, this. Now let us find the gradient of this function and see what it comes out to be. Gradient of this function is equal to partial of this function with respect to x1, partial of this function with respect to x2. Now, look at this. If I take a partial derivative, means x2 doesn't change. What is the derivative of x1?
2x1.
2x1. And the derivative of, with respect to x2 is 2x2. And you observe something very interesting for a circle. And this happens to be just pointing in the direction of twice just the p vector, isn't it?
The radius.
P is your p vector is given by x1, x2. Are we together? Right. So what does it mean? Where does the gradient point? Gradient is just a vector that points. This is gradient of fx1, x2. Isn't it, guys? So far, so good, guys? Now, there is an interesting lesson. If I look at lots of circles of different, these are all, the functions have different constant values. So you would agree that along the circles, the function has to be constant, right? Those are constant value surfaces or constant value curves for the function. What is the gradient point relative to those circles? What is the direction of the gradient? Is it parallel to it? Is it inclined to it, or is it perpendicular to it?
Perpendicular.
It's perpendicular, isn't it? So we notice the fact, that, let me write it in a different color so that this is emphasized, or maybe I'll use the same thing. Observation. The grad f, let me write it as x vector, is perpendicular to This is the symbol for perpendicular to the constant curves. These are called contours, right? To the constant curves, i.e. the circles is some constant r squared, right? For some r. Isn't it, guys? This observation is very general. The point is, what is true for the circle is always true. This is a general fact. Right? Gradient of f is perpendicular to contours of fx for any and every function. This is a very general fact. I use the example of a circle to illustrate it, but actually this is a very general fact. It's a thing you need to remember in mind. Well, that's a long detour. So where are we going with all this math? That's why all these mathematical preliminaries. So here is where it is coming from. So let's go back to our energy surfaces, our sort of error surface, rather, error surface. This was a beta naught, beta 1. These were our this thing. So here, do you notice that you had these contour surfaces, right? Also observe something. Where does the gradient point? The direction of the, first of all, it is perpendicular to the constant surfaces. But is it pointing in the direction of increasing f value or decreasing f value? Does the value of f increase as you go in the direction? Like what does the radius increase as you go outwards in the direction of the gradient, or decrease? Increases, isn't it? In fact, it increases the most. Perpendicular to the gradient is, of course, the constant surfaces. So the second observation is perpendicular to and every f, and points to the direction of maximum increase of fx at that point. It's a very general observation. The gradient points to the direction of maximum increase. So you want to increase a function, follow the gradient. If you want to decrease a function, go against the gradient, because that will be the fastest way to decrease a function.
Gradient descent.
Gradient descent. And therefore, when in our case, what do we want to do? We want to decrease the error. The error. So we go against the gradient, right? In other words, if you are at any given beta value here, let us say that this is some arbitrary p given by beta naught, beta 1. What is it? What do we want to do? And this is the perfect beta naught tilde, a beta 1 tilde. You want to go here. What is the way to go there? What do? You will say beta naught's next value should be equal to the previous value of beta minus alpha times. Yeah. So in vector notation, you can go, if you write just beta minus the gradient of the error function, right? This is the equation, the celebrated equation of a gradient descent. That is essentially the heart of machine learning. The learning of machine learning often amounts to the gradient descent towards the minima. That is why I took some time to explain this concept, because it is not just a concept in machine learning. It is one of the concepts central to this field, right? It's the gradient. So if you break it out into components, you could say that beta 1 or beta 0 next 0 next is equal to previous value of beta 0 minus a DE D beta 0, beta 1 next is equal to beta 1 minus alpha DE D beta 1, right? And so forth. You can keep going down to other values of beta n. Let's say suppose you have beta n next is equal to beta n minus, suppose you have n-dimensional space, parameter space, beta n, right? It's just a generalized, it's just this thing rewritten in simpler, broken it out into components. This is your gradient descent. This is how you solve the problem. Now, let's come back to the machine learning part of it, right? This was a detour through calculus, basic calculus, right? We took the detour. Now what happens is, and I'll mention this without giving a reason why, when you take high degree polynomials and when you have overfitting, when you take large n for polyregression, what will you end up with? You will have beta 0, beta 1, beta n, isn't it, guys? You will have different parameters, beta naught, beta 1, this thing. What you observe, they tend to get very loud or large, right? So what will suddenly happen is your beta naughts, good values of beta naught will be, let's say 2, minus 1 or something like that. But these values, they will suddenly start looking like minus 1, 5, 7, 9, 6, 3, right? This will look like plus 168, 2, 1, 4, 2. Do you notice that these values of beta, they blow up? The values blow up. Right? So every factor seems to matter a lot. Each of the parameters seems to matter a lot. It seems to become very loud, you know, very large values. Geometrically, and I wouldn't give a proof of this, but just take it as a fact that this happens. So what does it mean in real terms? It means that if you look at the error surface, this error surface, right, it just runs away. The minima here is very far from the origin, runs away from the origin. That's the problem. And that is what causes, this causes oscillations. This causes the oscillations we observed for large n, right? Overfitting is there, high variance are terms. So what does it mean? If you go and look at this curve, let's go and look at this. Where are we? Yeah, let's go back at this picture. What you will notice is that for the blue line, the betas are reasonably small, beta naught, beta 1. Where is this parabolic curve? For the red line, you'll have beta naught, beta 1, beta 2. They will be also reasonably small. For the yellow line, 4 betas, beta naught, beta 1, beta 2, beta 3. They'll be a little bit pronounced, but still reasonable. But by the time you get to green lines, your parameter values are big. And by the time you go to the pink line, your betas are really big. Are you getting that, guys? Right? They become really big, and that is what is causing oscillation. One is pulling it in positive direction, the Y value. One is pulling it in a very negative direction. Here, let's do it there. Right. So if you have very large values, you can realize with positive and negative signs, they are all pulling the y value in different directions, positive and negative. So you start seeing a lot of oscillations in the function. So what do we do to cure it? You basically say that we are not going to take the absolute minima that is here, of this function. Let me draw it out again. So what do we do? How do we solve this? So guys, I'll continue on for another half an hour. I want to finish this topic. It's an important topic. What happens is that if you look at this bowl, and our origin is here. Sorry, let me draw it here. Let us say that our origin is here. So you notice that this has run away here, very far off, right? Beta naught, beta 1, etc., etc. Imagine that there are lots of betas. This is your error surface, right? So here are the contour lines. What you can do is you can say, regularization says that we don't want the absolute minima. We are happy so long as we go a limited amount from the origin. Let us say that you set a limit radius r, and you say that around the origin, I will go only radius r, but no more than that. So whatever is the minimum value of error lifted out from here, wherever it meets the error surface, whatever error is there within this disk, within this space, is what I will consider. Let me draw it out in 2 dimensions. In 2D, in the contour view, what you have is this. And again, I'll just draw it as beta naught, beta 1. You're saying that I have a certain radius of a budget, r, right? And I am not willing to go or find a solution above it. But the real solution is here, very far away. And it has its contour lines like this. So, and then more contour lines go here. More contour lines go here. So you notice that inside the disk, let me mark the disk as this. Let me mark it with big fat strokes. Oops, that didn't quite do it. Yeah. Let me take this. This is where you want to be, right? There's one intuition I can give. In India, we have the story of the Ramayana. And there is a scene in the Ramayana, the Panchvati, in which, so the story goes that 2 brothers, one is a king named Ram, and he has a brother named Lakshman, and they're very, very close, of course. And Ram's wife is Sita. And now they are the good guys. And there is a demon called Ravan, who is always on the watch to grab or cause mischief. So Ram and Lakshman, the 2 good guys, they have to go out during the day. They're in the forest. They're in exile in the forest. And they're supposed to go out and hunt for food, find food, look around for food. So while they do it, Sita is alone at home. And there's all sorts of danger. So what Lakshman does, the brother does, is he draws around the house a circle, right? And that is our circle here. You draw a circle. This circle is your limit, and you just say that so long as you stay within the circle, you're safe. It's an enchanted circle. No demon and no bad influence can find its way here. Find its way into this circle, right? Can come into the blue area. Think of it like that. In terms of our regularization, what it means is that you don't go out of the circle, because you know that if the values of beta blow up, you will have overfitting. So you set a budget. You say that no, betas, all the betas must, the sum total of all the betas, the magnitude must be within this point, right? So you could pick any point here, but it cannot be more than a radius. Let me just put this here, the radius. This is the origin. It cannot be more than a certain distance r from that. So now the question is, you realize that above it is the error surface rising. You realize that this is the point of minimum error. This is your beta tilde here. This contour line represents, if you think about this, below this are these contour lines, right? They are mapping to these contour lines. So what happens? Every concentric circle, that is, the further you are in this concentric contour lines, does the error increase or decrease? They represent surfaces of greater or lesser error. This is the point of least error. This will be this error surface.
Increase.
Increase. But what you're saying is, so what is the point of the least error inside your circle? So let me call this surface EA. This surface is EB. This surface is EC. This surface is ED. So which of these, if you want to find within your circle a point which has the least error, which would be, would you agree that EA, all the error, so EA constant error surfaces, EA is less than EB, is less than EC, is less than ED?
Yeah.
Yes.
That is clear. So now I ask you this question. What is the point of least error? Not absolutely least error, which is here in beta tilde, but the least error within this enchanted circle.
EA.
EB.
Just at this point, isn't it? Let me mark this point as some point, this point, isn't it? This is the best I can do. Within the enchanted disk. We agree with this, right? Now let's think about this. At this point, see, this is a circle. We just realized that in a circle, where does the gradient of the circle point? So this circle is given by f beta naught, beta 1 is equal to beta naught square plus beta 1 square. And we can generalize. This is the equation of the circle. Does it make sense, guys? We are in the parameter space. So here the axes are not x1, y1, but beta naught, beta 1. So this is the equation of the circle, isn't it, guys? This makes sense, isn't it? And the circle is equal to some constant, r squared. Oops, sorry, r squared.
Yeah.
So far, so good, right? So now, what is the gradient of the circle? Gradient of f is equal to whatever. You can just say 2 beta naught to beta 1. So 2 times this. It would be at this point, which is, where would the gradient of this point? It would point
from
in
the origin to
increase, and it would point here. Gradient of the constraint is this, right? Constraint surface beta is this. Now, what about this error surface? You see that the error surface EA, let me go to the white color now. The EA, this error surface, this is a contour line of the error surface, right? Point.
Yeah.
Right? Where would the gradient of that point, which is the direction of maximum increase of error? Let me
opposite direction.
Opposite direction, isn't it? Let me use a color that would be visible in this. So I've used maybe green. Green might serve a purpose. Let's say green. Yes, let's take this. So I'll just make it like this. So this would be the gradient of the error surface. Would you agree?
Yes.
The gradient would point like this. And so you observe something that you observe that gradient of F and gradient of E point in opposite, did I spell it right? Opposite directions. Opposite directions. Right? And so we can write gradient of F is equal to minus the gradient of E, but we don't know what the magnitude is. So we'll put a lambda parameter here. Right? So far, so good, guys? The gradient of the constrained surface and the gradient of the error functions, they point opposite to each other. Then there must be, with an up to a negative sign and a proportionality constant, this must be the equation. This is how you write two vectors which point in opposite directions. Up to a proportionality constant, they should look like this.
Yeah.
That's right. So it turns out that what I just showed you is not just true of just error functions. It's true of any function and any constraint. Here I made the constraint into a circle. You could take any constrained surface, right? And you could take any function. The optimal point where these two surfaces touch, just like this, they glancingly touch, tangentially touch, and represents a point of the best you can do, is always given by this equation. And it was discovered by the great mathematician Lagrange. I hope I didn't massacre. Is it Lagrange or Lagrange? Could one of you please verify? I think it's Lagrange. Oh, no, it's not. It is just L''Grange. Oh, goodness. I should know this. Could one of you please verify and tell me which is the correct one? So it is the Lagrangian. You say this is the Lagrangian multiplier. Maybe it's Lagrange. Lagrangian. Multiplier. And what
Lagrangian, Lagrangian multiplier.
Yeah. So the name is Lagrange, isn't it? The person Lagrange,
Yes.
the mathematician Lagrange. So you typically pronounce it as Lagrange, or at least I do. I don't know if that is correctly. The mathematician. He was a great mathematician. He discovered not just this. His work is prolific in calculus and analytical geometry and analytical analysis. So this is actually what I did is using the example of our error surfaces and constraint and regularization. Actually, I took you guys to the discovery process of a fundamental result in calculus. This is, in fact, constrained optimization. This is it. Optimization. And so what you can say is this is constraint optimization. And when you do it, when you apply the disk, a budget, a unit circle. So let us summarize. My spelling is getting more atrocious. Summarize. With unit circle as constraint, right? As constraint, right? You get error. We can find the constraint. We can find the minimum error within the circle. Within the circle, right? That is the solution we will take. So let's explore this a little bit more. There's some very interesting consequences with this. So we have constrained E this is equal to minus, okay, I think, I don't know which way I put the lambda. I put the lambda on the E. Let me do it the other way around, actually, because that is much more conventional. Let me put, it doesn't matter, right? If we are just defining the lambda, so who cares? Lambda multiplier. Typically, you put the lambda on the proportionality constant here, right? So I'll put it here. This is more traditional, right? Are we together? You put the proportionality constant on the constraint surface, not on the main function. So it is here, it is like this, lambda, and it is, by the way, just convention, nothing more. This is it. Now, let us rewrite this equation. What we are basically saying is E beta plus lambda F beta. Gradient of this is 0. This is what we are trying to find, isn't it? I just rewrote this equation. Yes. And from this, we conclude that, in other words, we are minimizing E beta plus lambda F beta. This, right? What you call it, see, error function we were minimizing before. Now we are minimizing a different function. This is called the loss function in machine learning. And now you got introduced to your first loss function, which is not your sum squared error. Actually, we did. There was another one in logistic. Did I do the MLE derivation? Otherwise, in mathematical methods, we'll of course do that. Function. Loss function. This is called the loss function. The word loss function is pretty pervasive in machine learning. And so today you got introduced to the loss function of this problem. This is the loss function. So let us work it out. What does it become? This is what you try to minimize. So in other words, now you say solution, the optimal point is where point beta, let me just say, this is, forgive me, the point beta tilde is where achieves by the way, do you notice that I'm using a very scripted L, right? I'm not just writing it like L beta. So it is much more common to use this calligraphic L for the loss function, right? Mathematicians tend to use the calligraphic L. If you use just ordinary L, that too is used, but more common is to see this calligraphic L used for the loss function. Loss function is one of the most important constructs in machine learning. You can say that machine learning walks on two legs. First, I told you that you quantize the error, and then you decrease the error. Now I'm extending it a little bit more and saying it's not just the error, it is a loss function. In any given problem in machine learning, you first write a loss function. Once you have written a loss function, then you can do gradient descent on the loss function to find the minima, right? So use gradient descent to find beta tilde. Beta tilde is arg min beta for the loss function, right? For this, it is that value of the beta that will minimize the loss function. Are we together? And this is a core result. This was where the long journey was coming to. This result is not just true of the topic at hand. It is generally true in a wide variety of situations in machine learning, as we will realize. Huh? We just did constraint optimization. Now let's look at it. Remember that I told you many Minkowski norms, different. Now recall the various distance. Do you remember that from the last discussion that we did, that there are many different ways of defining distance, the unit circle. I will go back to the top.
The Manhattan distance, Euclidean.
Yeah, that's right. I will remind you that we did this. Did I do it in this one? Or I did it, yeah, this one.
The
Yeah, there it is.
L1, L2, yeah.
L1, L2 norms, etc. So this is it. Yeah, L1, L2 norms. Yeah, we were talking about this distance notation of norms. So we will go back to that and ask this question. I'll just recap what we learned there. So do you guys see that, all these ideas tied together in machine learning, right? You may say, wow, it's such a vast space of theoretical constructs, but you would be pleasantly surprised to know that pretty much if you got here, as far as practical machine learning is concerned, this is all the concepts you really need, right? A loss function, gradient, and its gradient descent, that's all. That's all you really need in machine learning to a large extent. We'll come to that. So what are the Minkowski norms? If you remember, the Minkowski norm of 2 points was x prime was equal to xi, x1 minus x1 prime to the power L plus x2 minus x2 prime to the power L. This, the whole to the power 1, right? Now comes the surprising thing. Look at this little desk that we made in the Lakshman Rekha that we drew here, the yellow line. This is a unit circle, isn't it?
Yeah.
What is the definition of a unit circle? What is the function definition? For L is equal to 2,
2. Yep.
the fx 1. So now let me write it in the language of beta because we are in the parameter space. Beta naught, beta 1 would be beta naught square plus beta 1 square, isn't it? So the constant values of this function were the circles. What is the gradient of this? So, well,
Beta naught plus beta 1.
You already did that before. So this is it. Do you notice that? And what was error? In this thing, in the loss function, if you remember, the loss function was equal to the error function of the beta plus lambda f beta. And let us replace it with what they really were. The error beta was actually equal to, going back to the old story of where we started from, it is y minus yi minus yi hat square. Remember, y hat beta naught plus beta 1 xi, yeah, square plus lambda. Now what is fx? Beta naught square plus beta 1 square plus this, right? And wow, this is the equation that people write in books. Though I would highly recommend that you think in terms of the way I taught you, as a constrained surface between an error that you want to minimize given a certain constraint. This is the constraint. And now your book essentially writes this equation without, and there is a pictorial explanation for it. So this is what they're trying to say. Right? I've given you a much more detailed picture of this, and you write therefore L beta is equal to sum over all the data terms of yi minus yi hat square plus lambda sum over beta I square. This is beta j, right? Beta j means j is equal to 1, j is equal to whatever number of dimension there is, n dimensions, right? Sorry, whatever degree of polynomial you're taking, beta naught, beta 1, beta 2, beta 3, whatever. J is equal to 0. Does this look like it? So when you use n is equal to 2, this is called the regularization. Then you say, all right, that is fine. But what happens if I take L is equal to 1, right? Then the L is equal to 1 Minkowski norm means what? Remember, what does it do to your constrained surface now?
It became a diamond.
Yes, becomes a diamond, right?
That's it.
Diamond, it becomes a diamond. So let me go back and color this diamond. Big, bold strokes. Okay, I think I'll have to write it. So now in this world, it is still, remember, this is a circle. It's a unit circle, isn't it? It looks like a diamond, but because of the L1 norm, this is how a circle would look. All points on the boundary are unit distance from this origin. If you define your distance by the L1 norm, right? This is where we go, and this is your thing. Let's go back and draw our
The contour lines.
Contour lines. Where do they seem to touch?
Corner.
They
The
seem to
axis.
touch on the axis. This is something very interesting. This is the x1 axis, and this is the x2 axis. What happens is, more often than not, this pointy edge, notice how the pointy edge of the diamond pricks the error surface, error contour surface, isn't it? This is your point that you're looking at. It's no surprise actually that very, very often, because it's sticking out. If you have your, imagine walking into the bar and you have your elbows like this. Have you ever tried doing that? Imagine walking into a crowded bar and you have your elbows like this. What will happen?
You'll make friends, not.
Yeah, yes, exactly. You will hit a lot of people and annoy the maximum number of people that you can. So that is it. So these are the elbows sticking out. So it is much more likely to hit the contour surfaces, the contours of the error, contour surfaces of the error in this space, in this plane. And so what it means is, now what happens when it hits it? What is the value? So by the way, this is not x1, x2, I apologize. Remember, we are in the parameter space. This is beta naught 1, right? Beta 1 in this space. So what does it mean? At this point, what is beta 1? At this,
It is 1, 0, right?
yes, exactly. So what will happen is, at the optimal point, beta naught will be some value, right? And beta 1, that will be beta naught tilde, and beta 1 will vanish. The perfect value of beta 1 will be 0. Do you see this, guys? This point is beta naught tilde and 0. So what does it mean in terms of our equation? What it means is that y as a function plus a beta 1x, what happened? This term just disappeared, right? Means x doesn't matter in effect. So now the way it really works is not like this. The way it works is, let me just call it, deliberately I'll cheat. Let me go to n dimensions. It's a polynomial of n dimension, right? So they're n dimensional space. So beta naught plus beta 1, let me just say beta nth dimension, right? Beta 1x plus beta 2 x square, x square, x to the power n. What will happen is, when you hit it along this axis, a lot of the betas will start disappearing, right? So what will happen is, out of the betas that you have, beta 1, beta 2, beta 3, beta n, beta I, let me call it beta j, beta n. What will happen is, because you punctured the contour along this, some of these, right, betas may start disappearing. And your problem therefore reduces to a lesser number of terms in the equation. Do you see that, guys? And so what will happen is your model will be simpler. Not only that, you have done
Start smoothening up.
dimensionality reduction as a side effect. You have done dimensionality. In what sense? You said that all of these higher order terms mattered. They don't matter, right? Reduction. And now let's generalize it to many variables. Let us say that you write y, suppose you write y as a function of beta naught plus beta 1, x 1 plus beta 2, x 2. You know, this is really a different feature.
Yeah.
This
Limits.
particular regression, the L1 norm, will start destroying some of these features, right? So you will get, it will say that those features don't matter, you can get rid of it. What does it mean? You have reduced those features, removed those features from your feature space, therefore you have reduced the dimensionality of the problem, right? This is actually one of the great benefits of L1 norm. There is a name for this, it is called the lasso regularization. Surprising that it is actually, well, ridge regression was discovered a long time ago. Lasso was discovered somewhat more recently. And the authors of your textbook, actually, they have done considerable amount of work with the lasso. They even have a book on lasso regression. It's just L is equal to 1 norm. And so your beta function is, this is y minus y hat square summed over I. But what is your function now? Plus lambda, remember? What is your function?
Yes. Because
Beta 0 only.
This is equal to, the unit circle is defined as beta naught absolute value plus beta 1 absolute value plus beta 2 absolute value, so on and so forth, right? So I can write this as L beta hat is equal to sum over I, yi minus yi hat square plus lambda summation over beta j, absolute value j is equal to 0 to j is equal to, suppose n dimensions, right? Whatever number of dimensions that you take, it will be this. And so when you minimize, this is the loss function for lasso. This is your loss function. See guys, these things are given in books. Typically, it writes the equation, and quite often you don't know where the equations are coming from. Right? So I went through the derivation. Now, why did I go through this long mathematical derivation? Loss functions are at the heart of machine learning. And quite often loss functions have constraint terms and so forth. So I thought that if today I introduce you to how people create loss functions, how they reason about it, how they think about, and find ways to improving the model or regularizing it or doing things, you have gotten to one of the key activities researchers do in machine learning. Okay? So loss function for lasso. And this is, I promise you, the most technical we'll ever be in our machine learning workshops. But do this much level, do please try to understand, because you need this much. If you really want to be good in this field, you should know the foundations. And these are the foundations, right? So you should know that. And by the way, all of these things we will review again when we do the math of machine learning, right? Here I'm more focused on the regularization aspect of it. So this is the loss function, and it has a beautiful effect. What happens is that there is this regularization parameter, you know, this lambda. What lambda does is, as you increase lambda, the value of the different betas, they begin to go to the, let's say that they start with certain values. They go they go across, right? Or let's say that you normalize, actually, let me take a more normalized view of it. Let's say that they all start at some normalized value at the origin. this betas. So what will happen is some will fall to 0 here, some will fall to 0, and some will, lot of them will fall here, some will go here. So suppose you take a cutoff of beta here, this point. Suppose you take this as a cutoff. So what will happen? At this cutoff, these values, these betas will disappear, right? These betas, these features will, because each beta is associated with a feature, these features will disappear. Why will they disappear? Because their coefficients, their parameters have all gone to 0 at this value of the lambda. So what you do is you choose your lambda wisely so that a few at this moment, this particular beta is alive, this is alive, and this is alive. But these ones have all gone to 0. So you do dimensionality reduction by sliding lambda back and forth, right? Sliding the lambda back and forth, and you get certain feature reductions. Go ahead.
Asif, in this graph, you are assuming that all the betas are kind of in the beginning when the lambda is 0, they're same. But ideally they will be different, but still the effect will be same.
No, whatever their values are, yeah, they'll be different. One way to normalize is divide everything by its.
Oh, okay, normalized values. Okay.
Just normalize it to 1 and then see.
Oh, okay.
But in reality, see, I drew that more complicated picture, but let's go with this. Huh? So this is what happens. You have dimensionality reduction. So we learned 2 methods. L2, which is more common, is the ridge. It's called the ridge regression. DGE, ridge regression. Ridge regression. Been practiced for many years. Here, the constraint surfaces is sum over beta I square. L1 lasso regression, if you want to use this, f beta is equal to sum over the absolute value of I, remember Manhattan distance, unit circle of Manhattan distance of this. So this is it. And it's quite interesting that if you understand Minkowski norm, you understand both of these ways of regularization so easily. Not only that, you can cook up more regularization methods of your own. For example, why not try this? Why not try L3? I mean, you can do whatever you want, basically. Now, one of the questions that arises is, which is better? They both have their advantages and disadvantages. Lasso has one advantage that certain features just disappear. You have dimensionality reduction. Ridge will never make the features disappear. It will just make it very small because it's circular. So all the betas will have some more or less non-zero value. The ones that really matter will have bigger values. The ones that don't matter will have smaller values, but they won't disappear. So that is one of the downsides of the ridge, people say, but you don't get the dimensionality reduction benefit. But the problem with lasso is that it over suppresses, right? It is too pointy. Sometimes it gets rid of too many features, right? And so what people do is between L1 and L2, again, you have to try and see which gives you the best cross-validation error. There is also elastic net. What does it do? It basically says, get a loss function with both L1 and L2, right? So then you end up with 2 lambdas, right? 1 lambda 1 associated with lasso, 1 lambda 2 associated with ridge. And so you try to optimize this. Now you have 2 hyperparameters to search for. So elastic net is a very obvious extension. It says in the loss function, go add both the terms, both the Minkowski, L is equal to 1 term and the L is equal to 2 term. That becomes elastic net. So guys, this weekend on Saturday, we will do a lab in which we'll see the effect of all of this regularization. So guys, today, I developed or recapitulated a lot of math. We took a lot of time recapitulating the math, which we have done in the past, but we needed it today to understand the regularization. But once you understand regularization, let me summarize. Higher degree polynomials, without regularization, they tend to oscillate, right? Data. You can suppress it with more data, which is the best way if you can, but quite often you can't have enough data. Data is rather an expensive commodity. So you have another technique of constraint optimization, right? And again, as I said, in very, very complex models like deep neural networks, it is a given that the parameter space is vast, hundreds of millions of parameters. And even if you have hundreds of millions of data, it's still not sufficient. So you need regularization. You need the technology of regularization and constraint optimization. So that is given by putting a disk around it. So we went through the whole explanation of what is gradient descent. Some of you asked for it, so I did the recap of that. Right? So at any given point, the function achieves a minima. You go in the direction of the minima if you walk against the gradient, right? And we saw that both in one dimension effects and in multiple dimensions. Gradient points opposite to the gradient is the direction of maximum increase. So if you want to quickly decrease, you go against the gradient. If you're in Mount Diablo, the last thing you want to do is go against the gradient. What will happen if you go against the gradient?
Increase that.
You'll tumble down the hill.
Yeah.
Isn't it? Because gradient is the steepest path, right? Up the hill. You don't want to go the steepest path downhill, because the steepest part downhill probably means you're falling down. Okay, so this is it. This is what we are saying, that when you have a constrained region and you say, give me the minima here, then at that point, the minimal point, optimal point, the gradient of the constrained surface and the gradient of the actual error function will be opposites. So in other words, you can write it in this way. Error is up to a proportionality constant and a negative of the other one. And that is essentially the equation of Lagrange multipliers. This is called Lagrange multiplier. At some point in calculus, you must have learned this many, many years ago in your calculus. Anybody remembers learning this in calculus? So, but if not, then well, today you learned something very important. It's constraint optimization thing. And so regularization is as simple as saying, what if my constraint surface are the Minkowski norms, unit circles with different Minkowski norms? That's it. All of regularization can be asked in one simple statement. What if I apply a constraint surface, constraint in the unit circle constraint in the parameter space, in the hypothesis space, that the values of the parameter must be within the unit circle. The moment you do that, both of the regularization come like this. So in other words, if you were truly a very, very skilled mathematician who knew all of this theory very well, the way to explain regularization to that person would be, oh, it's constraint optimization in the hypothesis space of the error function. The constraint is the unit circle with different norms. That's it. Right? So that gives you your lasso and your ridge regression. So that's what I meant. That's a summary of what I am saying here. Elastic net is the hybridization of the two. So I would like to stop here.